Okay, and also I'll do a quick introduction to you. So, hi guys, today it's our great pleasure to welcome Dr. Michael Greenwood to share his research and insights with us. And Dr. Greenwood is a research scientist and group leader for the Computational Research Group at Natural Resources Canada CAMMET Materials. So currently, Mike is leading efforts to integrate AI, high-performance computing, and automation into material research workflow to accelerate material discovery. And Mike, we are excited to hear about your groundbreaking research. Now, the floor is yours.
Yeah. Okay, great. Thanks for having me. I was actually hoping to do something completely different, but as it goes with terms of programming and time, it never completely works out. So I've kind of fallen back a little bit onto a previous presentation I did on digital automation and just some of the workflow development we've done, but tying it in with some of the newer research where we're kind of applying this, and that particular focus is going to be on carbon capture areas. So it's kind of broken down. It's kind of more like three little talks. One is just kind of an introduction to myself, some of the research we do at the ChemEt Materials Lab here, specifically towards what we're doing in terms of self-driving labs, and a little bit about me. Then we're talking a little bit about the digital infrastructure, and then kind of focusing on how this digital infrastructure development and kind of new model development around, we'll be applying it to one of my projects, which is on direct air capture for CO2. And how we're doing like AI and simulation integration in with the experiments, and so that the AI models can basically learn from both of those. But before I did that, just in my thing, my first foray into AI, because there's a whole caveat to what I'm about to say, is that technology changes very quickly. And a lot has changed in the last few years, especially around large language models. And I just kind of want to use this as an example. So back in what was it, 1999, I did my first course in artificial intelligence in my undergrad as part of my computer science. And my project was, I decided instead of doing a tic-tac-toe program like everybody else was going to do, I was going to build an expert system that would do first year physics homework. So this involved basically the goal was to ingest information about a question. So basically the system would ask you questions and narrow down on what the problem is you're trying to solve. And then it would go through and it would use searches, and it would have rules around algebraic operations and search through them and step by step show you the instructions based on its database of equations, how to actually solve your problem. So this is basically an expert system tied in with search trees that would actually show you not just what the answer was, but how to do it. But now you can go to ChatGPT today, you put in the problem, and it basically does exactly that in a couple minutes, as opposed to me having a very complicated thing. So what I'm going to be proposing is there's what we've developed since I think it was 2017 when we first started talking about self-driving labs and how we're going to do data management infrastructure and how we're going to store data and kind of feed it into AI models and how AI models are going to play around with it. Some of that may be up in the air in terms of what we've done in development. Some of it will still be core because traditional databases are still very reliable, but how maybe we interact with them may change as we go forward with new large language models. So currently, I don't just do this. We actually do a lot of different projects. So when we're working at our lab, we're expected to work on a variety of different projects. Some of them were project leads, some of them were consulting, and some of them were kind of in the middle where we do some development work. So currently, I'm doing basically works where we're doing battery recycling in two areas. One is chemical leaching, where we're actually developing another self-driving lab in collaboration with NRC Mississauga. And so this is a rather large project because it actually involves developing two self-driving labs, one for the chemical leaching and the other one for subsequent crystallization to recover the materials from the solutions. We're also doing work in laser melting recovery. So basically the idea is you take black mass, you compress it down, you superheat it with a laser, basically you get evaporation, and a lot of the metals like cobalt will just kind of melt and form into balls, and you just basically recover it directly from there. We're doing additive manufacturing of metals, so we're tying in AI into here and modeling to basically simulate how the process parameters would affect the microstructure, and ultimately how that microstructure would then link to fracture susceptibility to prints, so that we can try to accelerate new additive processes for new alloys in how we can have different processes. Related to that is turbine repairs, which is basically welding. So we're tying in various microstructure models there to basically do digital twinning of welding processes. And so welding, additive manufacturing conceptually is basically the same idea as welding, except just happens at a much, much faster cooling rate scenario. The one I'm going to talk a little bit later on is on carbon capture, which is direct air capture. We're broadening it out to also include point source capture, but the focus is still direct air capture because we're not going to consider impurities that might happen in point source capture just to reduce the complexity of our initial system. But when we're building our models and our AIs, they'll still have the capacity to be able to deal with the point source capture. We do projects in alloy optimization. So then right now we're focusing a lot on aluminum. So we're collecting large data sets, training models, and trying to do kind of active learning processes, not with self-driving labs, but just through like traditional manual experimentation, and just kind of driving how we can choose what alloys to do in these high dimensionality alloys that are now starting to come out, where you get 5, 6, 7 components to your alloy. And another one, which is directly related to the carbon capture, is in hydrogen pipelines. So permeation of hydrogen becomes very important. And so there's an overlap with the carbon capture project, where we have basically are doing control systems and automation for moving gas through permeation cells. And so there's a huge overlap there. So those kind of two tied together. When you're working in a lot of these different research areas, you tend to develop a lot of different technology usage areas. So I started when I coming out of my graduate work, I was a phase field person. I was a programmer that would do high performance computing. I do adaptive meshing, a tiny bit of AI, but what I would call more classical AI, where it involved like basically search trees and kind of those kind of architectures, rather than more adaptable machine learning and neural networks. I didn't really touch, like I did some courses in my undergraduate in database management, but never really touched them. And so then as you start getting more and more projects, you start bringing in more tool sets, you become more familiar with things like finite elements, fluid dynamics, get into atomistic simulations, doing MD, DFT, phase field. Then you branch out into different AI techniques, like to where you're doing generative models, reinforcement learning. Haven't really done a lot of classification. Looked a little bit at image segmentation, but it hasn't really been that important to us yet, so we haven't really gone down that road. And then I've been doing a lot of database programming, API development, and front-end development as well. But generally, we take a pragmatic approach. So we keep it as simple as we can, but at the same time, we also want it to be modular and reuse, so we don't have to reinvent things over and over and over again, especially when we see something like self-driving labs, which we can build a common infrastructure that all of them can use, as opposed to rebuilding the same infrastructure for every individual SDL. So just it's kind of one of the projects that just to show a case very quickly, we do for the solidification model development and tying into digital infrastructure. We're basically building links and automation for a number of different models. So this could include crystal plasticity, there's thermal finite element simulations, and then phase field microstructure simulations, and tying into experimental data, so that and eventually we will actually want to build a self-driving lab around welding as well. Although we don't have funding for that right now. We're hoping in the next funding cycle we can get something to kind of build out on that. But the idea is basically you have a finite element model, which can go around a pipe. You can get a thermal history for different weld beads. In the beads themselves, you can actually do phase field modeling of the microstructure. Similarly, in the heat affected zone, you could do multi-grain simulation. You can do multi-phase if you want. There's a lot of different models out there that can be implemented and eventually integrated into basically a library tool set, which can then be pulled for various scientific applications. So some of our SDL work that we're doing at NRCan, it started out, we were intending to do one, and then it grew to two, and now it's 6, and there's even talk about doing more. So right now we have ones which are focused on thermoelectric material development. And so this is looking at optimizing electrification wires for electric vehicles. So trying to optimize the electrical conductivity, but also maintaining a certain mechanical strength. So you almost get like a Pareto kind of thing where we need to have a certain mechanical strength, but we want to do a trade-off in terms of electrical property. And so it becomes very important. This is a both chemistry selection and heat treatment process, because some of the heat treatments can be very complicated. The first one we ever did was the thermoelectric material, so we still haven't completely completed and closed the loop on that one. But what we have is basically a generalized casting module, which I'll talk a little bit in a bit, where you can do chemistry selection and thermal processing just to link to the microstructure. The one we're working on now, which is a large project in collaboration with NRC, is the battery recycling, where we're doing the chemical leaching, which is predominantly a process optimization self-driving lab. We're looking at doing magnetic materials, so finding optimal microstructures, process paths, and recycling of magnetic materials, particularly where it involves like a lot of the rare earth elements, as that becomes very critical in our modern economy. The one that I'm working on and we'll just showcase a little bit today is on the carbon capture, where we're doing basically a process selection and structure optimization. And then as we start developing new models, we're starting to automatically kind of incorporating them into our digital SDL infrastructure, just because it's very natural for models to be able to be automated in this way, and it doesn't, the overhead to do so gets quite low. So everybody likes to show this diagram. I'm never really big on it, but I thought I would throw it in. But I want to focus more a little bit on the right, just kind of thinking of how experimentation and even simulation has kind of evolved. And so a lot of people, you started with your manual trial and error experiments, everything's done by hand. Then you can go through and you can start thinking about how you're going to automate various tasks in your experiments and or simulations. So in simulations, it's easy. It could be as simple as, you have a big parameter space. You're just going to write a script to auto submit a bunch of your simulations. Experimentation, you can use gantry tables or various other tasks. If you have money, you can buy chem speeds and stuff like that, and you can automate individual components of it. And this kind of led, I guess, probably in the 80s through the 2000s, where people started doing a lot of like high throughput experimentations, where you're basically doing very quick individual tests of a subset of a whole experiment. And you could do screening and automation of those. Or you could start devising what's called combinatoric experiments, where basically you could do a single experiment, but you can have like almost like an array of different properties, and you could do like maybe a thermal test on one and then measure all the properties and screen out a whole bunch there. And that's kind of led into what's happening in the late 2010-ish, kind of driving to there, where you're driving to full automated test and characterization. And this is what our 2017 workshop was, where Alain Asper-Guzik at UofT was kind of the driver behind, is basically going to like fully automated closed loop systems for particular experiments, which is kind of AI integration. And this drives and could provide like a natural feed into basically this fourth paradigm, which is kind of the big data of it. So basically it becomes almost like a feedstock that is self-driving and self-propelling into there. But then you could almost imagine on top of that being, once you have that big data feed from all sorts of different self-driving labs and experiments, feeding into an even larger kind of AI-driven global optimization. So you can then start looking at policy implications or explorations across the board, like which battery recycling technique in a particular area or for particular material might be more important. So you could have an SDL around the laser battery recycling, and you can have an SDL around the chemical leaching. And maybe for one particular type of battery material, one is more energy efficient than the other. And then you can have an AI which is looking at those cross decisions and then indicating to different SDLs to do experiments. And you can just imagine it broadens and broadens and broadens. So what is an SDL? I've been throwing this around. To me, an SDL is very simple. It's basically a closed loop process. So basically, you have some essential components. Every step, to be truly closed loop, every step of your experiment or simulation process needs to be automated. You need to have, because it's now going to be automated and it's going to self-feed back into itself, you need data workflow management, whether that be local or remote. And you need some sort of decision maker. Typically, we would call this artificial intelligence, whether you're using traditional or classical, what I call classical artificial intelligence, or machine learning operations. Some way a human is out of the loop in deciding how to proceed to allow the self-driving lab to continue on if a human happens to not be present. You could consider there's, machine auxiliary components. You could say, okay, we could do machine learning, so it's a little bit more refined artificial intelligence. As I said, you don't have to use machine learning in this case to really create a self-driving lab, but it's kind of the modern acceptance that you would. And high performance compute integration. So you can do a lot of these AI models and data workflows on a regular desktop or a laptop nowadays, but some models may require more high performance, or you might get more benefit from integrating like supercomputer clusters into your workflow, either through data analysis or through the decision maker process. So when you're doing closed loop discovery, your goal is really to automate each step of the exploration loop. So basically you come in, you conceive a problem, you define a parameter space that your SDL is going to work on. You make a decision, and once you start the loop, you make a decision as to where in that parameter space you're going to test. That's what the decision maker comes in, it's going to make a decision. It has no prior data. It's basically going to be completely random for the most part. You're going to synthesize your test material, characterize its properties, measure performance, and then feed that back into whatever model you're using to make decisions. And it will just continue and continue and continue until it reaches such an objective. So what do we need? We need robotics, we need data infrastructure, we need analysis tools, because every little step has to be automated for this loop to work. So if you get a raw data file and you need to extract a linear fit, you need to build an automated tool which will go in, do the feature identification, maybe flag it if there's any errors in the data, extract the features, and then feed that subsequently in. And then you can build them modularly. So then you can get into like more complex workflows where you're on the right here considering more of a hierarchical workflow where you're basically doing a subloop, just like we just described. You can measure the performance, but at some point it's now going to decide, okay, now we're going to expand our parameter space and maybe work in a different parameter space. You can have an overarching AI which can make that decision. Or you can go in and you can have parallel workflows. So maybe you want to start incorporating simulation into it for whatever purpose. So you can have an AI which is learning simultaneously from simulations and from the experiments, however you might design that AI, but then it can make decisions and run on how to run those simulations and how to run those experiments and how to make the connections between the two of them. So when you start doing this, it becomes very important to follow modular design. So this is in the physical synthesis, in the characterization, auto analysis. We're going to do the machine learning decisions. So we decided that it was very important to build this library of all of these different tools. So for one example is going to be this casting map, where we decided the casting synthesis itself is a module, and we can then apply it to other applications where we started out with thermoelectric materials. Now we're looking maybe to apply it to high entropy alloys or to steel development or to aluminum development as opposed to just that. If we had built in the specifics of the thermoelectric material characterization directly into the robotic automation, we would have had to disassemble this, bring in the new characterization, or replicate it and do that. Having the modular system where you could just specify new chemistries allows us to really do that. So then we started saying, well, there's also some health and safety issues going on for some of these experiments. So do we want AI that's making the more global optimizations to have direct interaction and control the robots, or do we want to buffer that off? So those are some decisions you need to make as well when you're doing self-driving labs. So generally all of our self-driving labs, because we involve chemicals and molten metals, we have safety features kind of built into the control systems, and we interact through an API. So basically the AI will ultimately send an instruction that says, do this experiment. I don't care how you do it, just do it and then give me back the result. We also look at various simulation models. We take all of our phase field models. We start building wrappers around it so that we can build automation to it, phase field crystal lamps, density functional theory, and we start building out various analysis models as well. So if we develop a routine which can extract cyclic data and then find linear trends within that cyclic data, we can reuse that over and over. And then also as we start building out different machine learning models, we start with some simple standard ones like Gaussian processes, random forest, whatever. We built them and we just store them so that we can reuse them if needed, and then we can customize them and resave them as a new module. So when we get into closed loop processes, we start defining some various things. So we have our MAP, which is a materials acceleration platform. Basically, it's an SDL. I'm trying to get us away from using the MAP terminology and kind of just start using more the broad SDL. But a MAP is basically a predefined workflow that we never change. So it's basically a series of tasks which produce a particular output which you can then explore or optimize. Then we define what we call as a campaign, and a campaign is that parameter space that we said. Okay, so we said, here's your playground. AI, go ahead, you can work within this parameter space because maybe we've only loaded up certain chemicals, or we know for whatever safety reasons we can't go outside of a certain range, so we kind of constrain that parameter space to there, and then the AI can do as many loops as they want. An experiment we define to be a particular instance loop within that campaign. So it says we did this conditions with this chemistry and so on. So then once you've gotten that, then you start thinking, okay, so now we've got a simple process. We have a single process, and this is what most SDLs are today, is they're kind of isolated SDLs where you have a control system. You probably even build in the AI into the workstation that's doing the controlling. You're doing your workflow analysis, all your data analysis kind of on that local machine. And it's an isolated system, but that can lead to data fragmentation. So if you had 10, 20, 100 SDLs, all of them running independently, then you have 10, 20, 100 different data locations for all of your different systems. But it is easier to build and design. So we kind of took that in mind that, every SDL we're going to build is probably going to start like that. And so instead of trying to figure out how to integrate it directly into a higher level data management workflow orchestration, is we just define a wrapper which needs to go around it once you've completed it so that it can then communicate with an exterior system. And we just remove the AI and maybe some of the analysis from the local workflow and basically move it out once we've completed it. So our goal really was to develop this digital architecture where you can start segmenting off things like the AI, the data management, and the analysis. Our biggest challenge being in a government organization is there's a lot of network security. So sometimes there's some restrictions into where you can go. So we tried to centralize the orchestration through one system, which can then be secured, and it can communicate with everything. But the limitation of that is that it needs to initiate all transactions. So basically, it's monitoring all of your remote processes. Like if I have an HPC within my lab, and I have another cluster in Montreal, or I have a cloud data infrastructure, the data orchestrator basically is the one that's always reaching out to talk to the different locations. This cloud system could never reach in because of network protocols. The HPC could never reach in because of network firewalls. We don't want we could want it, but we just decided not to allow it. Is a local executor could reach into the data orchestrator to do it, but instead what we do is we have the executor kind of saying, I've completed my task, waiting for the data orchestrator to basically say, okay, monitoring, saying, okay, your task is completed. Now I'm going to pull stuff off and move it to step B. So really it's going to a very modular building system. So to do this, we kind of built in like 4 categories of services. One is the executor, which basically does specific task execution. So each executor could be a part of or a complete SDL. We have the data orchestrator, which is basically managing all of the interactions of the executors, basically monitoring when tasks are done. And if data is completed on, say, executor 1, it pulls it in and then moves it to executor 2 and tells executor 2 that, you have a new instruction. Here's your data packet. Do what you want with it. Then we have the archivist, which is basically monitoring the orchestrator, because the orchestrator is really a transactional system. So it's basically working on live data. Our data set's never gotten big enough that we've wiped it out, but theoretically, eventually we would clean up the data and we would only keep live data in it. The archivist basically is pulling it off to an offline system so that when humans or other AI models can interact, they're not going to really be competing with bandwidth that the orchestrator might need to do its operations. And then we have a human interface, which I've gone back and forth on various names, kind of landed on Insight, which is basically providing a platform for monitoring your campaigns, different map systems, building workflows. And it's kind of broadened out a little bit too. I started looking at ways to turn it into almost like a laboratory information management system to manage projects so that you can start building several SDLs or automated workflows within a particular project, just to kind of bring more human-centric collection of that. So I called it Franklin. My joke was that because of the way the government network architecture was, we named it after one of the doomed Northwest Passage expeditions, because we figured we probably weren't going to be able to make it work, but strangely enough, we did. But the idea is that Franklin will manage the task data transfer. But the data itself to Franklin is completely agnostic. It doesn't know what the data is for, what the units are, what the type is, and it doesn't need to know any of that information. It just needs to know that it's getting a data packet at point A in its workflow process. When process A is completed, it knows that process B needs to start and it needs to retrieve that data packet from it, and then it will shunt that data over to it. Executor, however, is the opposite of that, where is very specific and it basically executes repeatable tasks of specific operations. So it knows that it's working with a dosing device. It knows that it's working with a casting unit to melt down the material. It knows that it's working with a welder, and it will systematically go through. It knows it has a thermocouple, it's collecting it and stuff like that. So then it will then be wrapped around this API architecture that I kind of described before, so that it can communicate with the orchestrator. The archiving is just basically a service. It runs in the background. I'm not going to go into a lot of detail, but just monitors for changes in the orchestrator database. As new data is completed and experiments are completed, basically shunts it over. And then Insight, which is basically my dashboard, where you can kind of go through. You can in the automation section, you can start building in programming in new modules. Basically, what are the inputs and outputs of them? What type of data types are going to be there? Then you could build individual processes, which processes to me is a self-contained SDL. And then you could also have workflows where you can start linking different processes together. So you can have your casting module, which is one process. Then you can have your characterization module, which will be characterizing, say, the thermoelectric properties, and then maybe link into your AI module, which will do some AI analysis in that workflow. And maybe there's some other, which we call atomic executors, basically doing single operations, say, for data analysis, like doing linear fits or other types of things. And so you could kind of build this all from your resource library, which builds up over time. So if you're not familiar with API, we tried to simplify it as much as possible. So right now, you can really, when you're building these, you can write it for any API. So the orchestrator works on a number of communication paths that you can choose when you're building your workflow. The two main ones that we use is SSH. So we basically do things by SSH proxy commands. This is particular for systems like HPC, where we probably can't install formal APIs. So we basically create a local instance of an interface, and then it basically does SSH commands through that. But generally speaking, it basically works through a REST API, and there's a number of very simple instructions that the orchestrator deals with. I think there's a total of 8 that it only needs to operate. And one is basically to get like a status update where you can get errors, you can see whether that particular workflow step is queued, it's completed, etc., whether there's data. You can send instructions. You can then request, like once it's identified that it's completed, you could retrieve data, or if there's an error, you could retrieve log data. And then from the interaction side, the other side of the API is more for that front end where Insight kind of retrieves information to get overall information about experiments, campaigns, and your self-driving labs. And once you have this all in place, then you build your programmatic workflows. So I'm just going to quickly go through this. So you basically have different actors. So in this case, for the thermoelectric map, we had the orchestrator, we had the physical executor, we had a decision maker executor, which was just a simple Gaussian process routine, and some analysis executors, which basically analyze the raw data that's coming off of the physical executors. So you start building out your workflow. So you basically initiate your campaign, you define and store your constraints, define and store the optimization goal for the Gaussian process. It goes through like a systems check. It basically checks the remote systems of all of the executors just to see, are you there and are you operational? Can I start? You can also predefine stored data. If there's data in the archive for your machine learning model, you can indicate to it that it can use this data as a kind of a pre-training to work with. So basically, then it'll pull that data from there. It'll do the training. In this case, it was an explore exploit routine, and basically store the decision it made, and then basically sets up the first experiment. So basically, it sets it up in the queue. In this case, our decisions based on like composition. We have a temperature, holding time, annealing temperature, and annealing time for the holding time as well. So then it goes through each stage of the workflow and just kind of monitoring it to see if there's any errors and if there's any data that it needs to analyze. So the orchestrator sits over here. It's basically just looking at the status check. So this is where the thermoelectric map will basically do a chemistry dosing. And then it will go through a number of different steps where we do dosing, melt and solidify, we do annealing, we do a mass measurement, then we do an XRF measurement, and then we do a thermal diffusivity measurement. And basically the orchestrator in time is just following its workflow, checking the status. Once that status is complete, it will then, for example, if the thermal diffusivity measurement's completed, it will then request the data, send it off to the analysis executor, and basically it's just basically looking at a linear trend of the data and basically gives them some statistics based on whatever that's going to do. And it also does this for other things like the electrical conductivity once that comes off, and the Seebeck measurement. And then once it's collected all of that, then it goes through and it calculates this ZT factor, which is a kind of a combination of the outputs of all of those other ones. So it doesn't actually involve the physical executor. It's basically an analysis. And the ZT is what's ultimately we're optimizing over and gets back basically sent back into the archive for training. The orchestration database, we went back and forth a lot on what type of data we wanted to store. So we really store three types of data. So scalar data, basically single values. And this we thought about merging that with the textual data, but we decided to keep it separate because it allows it for more streamlined interaction with some machine learning models. I'm thinking we might simplify it in a future one. I keep going back and forth on it. There's textual data, so you can just store raw CSV or JSON structured data, whatever data format you want. The database itself doesn't care what it is. It's just a textual thing. Or for large data files, so when we getting into some of our simulations or machine learning models, we get into volumetric files or high resolution images. Certainly the same thing with microscopy. You can get very, very large images. Rather than bogging down the database, we instead store them in like a data lake type format, and then basically store logical links to how to retrieve those types of data. And we also store metadata, although the orchestrator itself doesn't really need any of that information for operations. But when it comes to human interaction, humans like to know that they're measuring a chemistry, for example, or that your units are in kelvins, as the orchestrator doesn't care. We then started parsing off how we're going to structure our archival data stores and what our workflow would be for that. So you got your typical map workflow, your decision maker. We have like cloud systems. We have physical simulator executors, cloud, and our data lake. And then we have this archival executor, which basically works within the orchestrator workflow as well, which is basically kind of monitoring and looking for new data updates. And separate from the map workflow, it will pull data and move it for archival purposes. And then we were building out simulation workflows. And so rather than building our own interaction with a lot of the queuing systems that are used on modern HPC systems, we've kind of leaned on Ada, which is a software which allows you to build simulation workflows on HPC systems, but it's got a lot of built-in tools to interact with things like PBS and Slurm and basically builds submission scripts. So we just kind of leaned heavily on that, wrapped it around so that it interfaces with the orchestrator so that we can now template any new simulation code, throw it into our template, and basically we can run things remotely. So generally, I'm going to shift away from workflow now, and we're going to quickly kind of go through the carbon capture and simulation integration. So really, there's three types of simulation integration. And there might be more, but these are three that I could think about. One is a hierarchical approach, where you're basically running simulations to narrow down the experimental exploration space. So you can basically pre-screen a lot of AI decisions, saying with some simulations, and basically reject them if the simulation says no, because your experiments are time consuming. You can have your parallel approach, which basically you're doing a digital twin of your physical process. And so basically you can then look at transfer learning. So you can or direct integration, and you can make a little bit more complex model where it can continuously learn both at the same time. And then there's integrated, which is basically providing complementary data that either you can't measure or is very difficult or expensive to measure. So one example of hierarchicals, if we did like mechanical response, we could do some FE simulations, kind of automate those, and you can basically run your FE, and basically if you had a hard stop on terms of, say, fracture strength for whatever material you're doing, you could do a simulation, see if you exceed that. If you don't, then you allow it to proceed to experiments. If not, you just tell the AI said no, and then just kind of proceed. Parallel processing, which is more what we're doing for the carbon capture project, is almost like a digital twin where we can do fluid flow simulations through the structure, measure pressure differentials, and then actually start incorporating adsorption models to see how CO2 kind of gets captured within the structure. Then we got integrated simulations where we're looking at, particularly for some of the welding and additive processes, if we move into the SDL direction there, where we start doing microstructure simulations linked with crystal plasticity, just kind of start relating process parameters to material properties. Because we know we're probably never going to be integrating our TEM or SEMs directly into self-driving labs. So we want to kind of feed in and see if we can do, say, microstructural simulations kind of as an add-on on top of the process properties to create more of a physical link to explain why things are happening the way they're happening rather than just doing pure optimizations. So for our carbon capture, I got really excited about this one because I really like the AI aspect of it. But to us, we've been discussing how we can use 3D printers because 3D printers seem to be a very natural way to build SDLs. So we're proposing with a UVic collaborator in how we can basically do CO2 capture. And I was kind of tying in how we could do SDLs and generative AI. So the basic principle is that you, instead of just having your resin in terms of a print, is you start mixing in your carbon capture material powder. So in this case, we're just looking at zeolite powder. It's a fairly common, inexpensive material that can capture CO2. People are developing other novel materials like metal organic frameworks that can be incorporated. So, but in principle, these other materials would also work with this process. So basically the idea is you mix it in with the resin in a sufficient quantity such that you can still do a lithographic print. You build your test cell, you run gas through it, you measure air in, air out, see how much CO2 you capture, feed that into a generative AI model, which kind of will adapt your printable structure. On the other side, in parallel, we can also do simulated fluid flow. So we can fluid flow, do adsorption modeling, assess the carbon and feed that in, and kind of build a model which is basically learning from both processes and kind of correcting in terms of the experiment. Because there's actually some parts of this, which I'll say in a little bit, that we realize makes it a little bit more complicated than kind of the macro scale that we get in terms of the simulation loop. So most people, when they're dealing with CO2 capture, are only considering this first one, was basically how much CO2 was absorbed when you pushed volume of air through the cell. We very quickly realized that the goal of these CO2 capture research, is they're trying to get the cost of direct air capture down from $300 per metric ton of CO2 down to 100. And a big amount of that cost is how much energy did it cost to push the air through. So there's the cost of production, but then there's the cost of how much energy did it cost to push the air through the cell per unit volume. So really what we're trying to optimize is not how much CO2 gets captured, but how much does CO2 get captured per unit energy. So the material aspect of a zeolite is that you get these very nanoscopic pores, like about 0.5 to 0.7 nanometers. And most of the adsorption happens on the surface. So we basically, any volume component to our print that doesn't get exposure to air in the cycle time that we're running on is basically wasted material. So that's the material cost. And then there's the complexity of the print, which can then impact your pressure gradient across your cell, which will result in an overall increase in energy cost because it's costing you more money. So if you printed a very dense open cell foam where you had a ridiculous surface energy, but you had to push the air ridiculously hard such that you have a huge pressure gradient across your cell just to move the air through it, then that you might have more surface area and capture more CO2 per cycle, but it may have cost you more energy. So it becomes a kind of a trade-off there. So we kind of defined a simple basic process, and we learned some things even just from doing some manual testing. So if you mix the resin and powder ratio, so then we realized you have a control of how much powder you mix it with the ratio, the resin. We can vary it, I think, and still be printable and self-sustaining in a range of about 20% powder to up to, I think it was 42% powder, at which point we stopped being able to print because it gets too viscous. We then print the proposed structure. We take the print cell out, we debind it in a furnace. So basically this is raising it to a temperature where we burn off all of the resin. The structure then needs to be still self-sustaining. That's where if you get lower than 20%, it will just collapse. Then we sinter it. So then we raise the temperature up between, say, 1,000 to 1,200 degrees Celsius. Sintering process just will structurally bind the zeolite. Then we take the cell out and we basically flow CO2 through to mix the in situ capture. So that's when we realized that when we do the burn off in the sintering process, the temperature and time that we do the sintering process and the amount of resin material mix we choose in the first place will affect the densification. And so while the nanopores are on the order of nanometers, there are also going to be micropores on the order of the zeolite particle size, which gas can do some surface penetration. So there's going to be some optimization that will potentially do there, which we're not presently simulating in the CFD. So for the project, we have, well, our primary goal, which is basically to find filter structures which basically reduce the cost of capturing carbon, which is our project specific goal. Second one is to basically build an autonomous research platform, which we also see applications in areas like defense. So if you want to build novel mechanical structure platforms, you can do 3D printing optimization of that. And then also expanding our capacity to create or adapt structures. So basically building out generative models and techniques for other applications. So our basic workflow, we start working through our workflow. We said, okay, what's our various processes and what are our bottlenecks? So our printing time, 1 to 2 hours, sintering time, 10 to 12 hours, and carbon detection, assuming our in situ system works, will be on the order of minutes. I know that the full cycle where they do direct air capture, or sorry, point source capture at least, has a cycle time of just 3 minutes. So that's where I'm pulling the minutes from now, but if we could do it in situ, we might even be able to do it faster than minutes. So our bottleneck really is on this sintering time. So this is where we start building out batch workflows. So basically it says, okay, we're going to, while our printing time is 1 to 2 hours, we don't have to just print one sample at a time. We could print several different structures in one printer. In fact, we could probably print between 10 to 12, depending on what our test cell size is, which lowers our 120 minutes down to 10 minutes, which is the same order of magnitude as the carbon detection time. And then the sintering time similarly. So like if you have 12 samples, you put them all in the sintering furnace together. You can't explore the sintering process for those structures, but at least you're just optimizing around that one structure and getting your batch time down to about the 10 minutes. So the basic idea is that we now need to build a lot of automation steps for all of the process, going from the SDL files, going into the print and doing in our thing. But then doing some experiments, we realized we have another problem where as we start doing our sintering and heat treating, we start getting cracking. So we're planning to do a pre-optimization, optimizing our thermal cycles and finding the bounds of our thermal cycles that reduce or eliminate the cracking of our sump structure. So it just goes to show that as you start developing these things, you're doing a lot of manual testing offline and trying to see where things are going. And then you find things that you weren't expecting and that may not have been accounted for in your workflow. So the idea being that we'd have an active material structure, goes in through absorption and desorption, measuring the CO2 output, and then feeding back into the AI structure. So Because I want to really build a more general optimizer, but knowing that that takes time and is higher risk because you never know, they may not work properly or work the way you think they're going to work. So we start with basically what I call a stage one generator. It's basically something that we know is going to work, but still gives you enough flexibility that you can generate different structures. And you can optimize within the parameter space of that structure. So it could be using some mathematical form, or in this case, we were having fun using one of my phase field crystal models to build some novel structures and then basically converting them and extruding them into three-dimensional channels that we could actually just optimize through. And then we're having fun twisting the shapes as well so that you can increase the surface area or interaction time of the airflow simulation. So then we basically built a virtual loop while we're building out the physical systems, just to see what kind of structures and patterns might be optimal from the simulations. But what I really want to build is a voxel neural network approach, where you basically generate some sort of voxel structure, which looks a little like Minecraft, and then basically goes through a smoothing process and other processing to ensure that it's kind of watertight and a continuum surface in terms of islands, and basically allow the AI model to kind of adapt this structure more organically, and not really limit it in what types of structures it can do. So then I started building architectures for progressive learning. So you could basically set up some three-dimensional CNN models. You basically train for occupancy just to get certain densities. Then you start saying, okay, we're going to flag areas that have no connectivity. So that basically these are not printable. And so then train it to avoid those. And then train for printability. So other things like when you're doing lithographic printing, if you're printing from the bottom up, so if you're basically this was your first layer and so on and so forth, then you're going to identify certain areas like these red dots, which are overhangs. Novelty is what I kind of identified here, so that they're not self-supporting. Because we're building a self-contained 3D structure, we can't build supporting structure to support the prints internally, because we have no way to remove those supporting structures because they're internal to the print. And then once you have a model for that, then we can transfer learn that and basically have it run through another model where we basically train for the property. And so for that, I was looking at a number of different models, GANs. Mostly I've settled on a reinforcement learning approach. And I'm looking at three in particular right now. One is basically a reward where basically it adjusts the voxel neural network directly. So basically what you would end up having in the end of this one is a model specifically relating your property that you're trying to target to the structure, so that it can produce any number of structures. This can involve evolutionary approaches. Another one is basically where you just have the printability structure, and now an RL model doesn't adjust that model, but it just starts optimizing over the latent space input vector to adjust the structure. And then a third one, which is what this little movie here is basically taking actions on the voxels themselves. So basically it's moving the voxels around to produce different structures. Right now it only moves it because it's trying to keep the same occupancy level, but you could do removal in addition as well. And that's basically the end of my presentation. I don't think there was anything in there that I couldn't share.
Okay, great. Thank you so much, Mike. And I think there's some questions through the chat. Let me see. Okay, so Atari asked the question that whether your data management work is publicly accessible.
Work in progress. So I'm trying to get IP office approval to basically release the data management framework so that we can make it publicly available and everybody can use it.
Perfect. And then you ask it like any thoughts on integrating LLMs to access safety concerns of the very advanced and capable platforms.
Yeah, Mike, I just wanted to ask about, I think it was the casting system. Anyway, the system with the automated um, powder handling.
Yeah.
I think you'd mentioned that obviously there's safety concerns with the powders.
Yeah, because like if we're using like for that particular project, we're using say magnesium powders. So then and depending on some thermodynamic constraints, like if you start mixing certain powders together, they could become very exothermic in reaction. And so we just have to be careful. So we wouldn't want like an AI model to come in and say, you know what, you can just dump raw magnesium in, or say aluminum with titanium, for example, and then you end up making thermite and it just melts through the crucible that you're using, which I may have done once. Okay, this is recorded, right? Not with the automated. We were actually looking at reactive systems, but what the idea is basically the idea is that you may have certain constraints that you want to ensure for, say, health and safety reasons, that you don't want to move outside of the bounds. That's one thing we're thinking about with the battery recycling map here. I'm just going to move this one, actually looking at the camera. So there's certain conditions, like if you start mixing in certain acids and doing certain stirring rates, you can get foaming issues, and you don't want the foam to kind of overflow the system. So you want to have checks and balances close to the experiment and not relying, because if the network gets delayed or failed, then you may get a delay and then the accident may have already happened.
Very interesting, thanks.
Yeah, thank you, Mike. So as Harry asked another question, like, does your orchestrator support experimental setup? If yes, how does it manage the wait times between experiments?
The orchestrator support experimental setups. I think maybe Vahid, you'll have to.
Hey, Mike. Yeah, maybe I can. So, from explanation, I was not basically clear if you are using the orchestrator to manage simulations entirely or experimental, basically experiments. That's why I asked this question. And
Yeah,
like even if you do it for different simulations, like for example, phase field simulation is going to take, let's say, 1 hour, another finite element is going to take 10 hours. So is this handling this in an automated way, or you have to wait for it?
It's handling it in an automated way. So it's basically the orchestrator runs simultaneous workflows in parallel. So like if you're running simulation A, B, and C, you have separate workflows. They don't see each other, but the orchestrator basically handles them, and it basically goes into a passive state and regularly checks to see if there's any updates from the remote executor. So the orchestrator doesn't distinguish whether it's a simulation or experiment. It doesn't have that knowledge. It knows where it is, like what IP address, for example, it has to go to communicate for the various workflow tasks. But it's set up to work with both experiments and simulations in parallel.
Oh, that's great. That's great. So it can work with both experiments and computation. That's nice.
Yeah. Yeah.
Okay, yeah, I really look forward to basically to publicly be able to access to the platform that you have developed.
Yeah, it's constantly under development. So one of the main drivers I'd like to get it publicly available is because then we can broaden it out. And if other people wanted to build on it and add functionality to it, because it started out with a small idea and it's kind of grown and grown and grown. And it's just a bandwidth in terms of getting all of the functionality we really want. And so if other people in the community want to build on it, that would be my ideal.
So if time allows, I have a follow-up question on the orchestrator as well. So with the optimization process, you are basically, when you want to optimize the progress, you want your LLM to be able to do contextual reasoning for you so that it can guide the optimization from a different perspective. Do you use LLM in the orchestrator right now for that perspective?
Not right now. That was my hint at the beginning, is that because we started building the orchestrator back in 2018, 19, before I had even heard of LLMs. I don't even think transformers were published at that point. So as technology changes, I'm starting to imagine different ways that LLMs can start interacting and even aid in terms of like some of the data management processes. But I don't think I
Right.
would deviate from having a formal database structure, but it's probably just more in how you interact with that database structure and the workflows.
I see. Great. Thanks.
Perfect. And because we are sort of passing the time, Mike, are you good with further questions, or would it better to contact you through the emails? Yeah, it's like.
If people want to keep asking questions, I'm fine. I don't have anything. I
Okay,
kind of
perfect.
cleared my day. So
Thank you. It's really interesting and cool topic. So I saw there's a question from Rafael. Would you like to unmute yourself? And you can ask directly to Mike.
yeah, I just saw
Thank
that.
you so much. Thank you so much. So I was wondering about the generative AI part of the workflow. Does that the architecture has constraints in the architecture so that the proposals are actually feasible? Something like, I don't know, physical informed neural network, something like that, that makes it that it can assure that actually the proposals given by the generative algorithm actually can be done.
Yeah, so in this case, I'm going very much. I definitely completely agree. Like, I hadn't really given thought to how you could do the physically informed component, but that aside, that's where the progressive training is kind of coming in. Is it's kind of learning this, like, to propose structures that would be printable. But even when it does propose a structure, because models often will produce things that might have a voxel at a place that just can't be printed. We kind of incorporated. There's a lot of software, and where there hasn't been software, we wrote our own software, which will go through and analyze the structure to at least ensure printability. And if we identify from a structure that there may be like one voxel at a place, or a certain percentage of voxels at a place, we could just basically eliminate them altogether. We would flag it back that it happened to the generative model. It can update its model to kind of self-correct for the future, but then we could still proceed with, say, the experiment and/or simulation.
Okay, thank you. Thank you so much.
I would need to think a little bit more what physically informed models we'd want to put in to do it. Like, there's other things too that we're considering that I didn't kind of mention, like do we have connective channels? Can air actually flow through? Do we have isolated pockets? And we're going to penalize like the reward functions if it starts producing isolated closed cells for our airflow, because they make no sense. There's air can't get in there, so it's basically just wasted space, even though it's producing surface area and stuff like that.
Thank you so much.
Perfect. So I think
I only started building this 3 months ago, so we were focused more on kind of integrating some of the more standard parameterizable models, and then I started building out. There are a couple papers on it where people have done some similar voxel generation approaches. So it's not it was novel when I had the idea, but now it seems like some people have scooped me in part, but not completely, because there's some areas that I still want to develop, so they've done some more infancy versions of it, which I'm happy to share if you're interested, Raphael, in the papers on that. I have some of those recent papers from 2024 where people have published on that. I don't know if that's your interest in area.
that would be really cool. And thank you so much, Mike, for sharing your insightful research with us. And I'll stop recording, and we